Okay, diving right in. Today we're looking at a tech that's got engineers talking, especially the ones working on those really advanced RF
Oh
systems.
yeah, definitely cutting edge stuff.
You sent over some interesting material about it. It's RFOptics 30 gigahertz RF over fiber mini L solution.
Hmm.
They're calling it a game changer. And our mission today is to, well, figure out why, what makes this technology so special, and how's it tackling those tricky problems in RF signal transmission, the kind of stuff that keeps engineers up at night.
Right, yeah, absolutely. And you found a really good set of resources too. The product overview, that detailed data sheet, and some stuff from RF Optics' own website, all about how they're using RF over fiber for satellite antennas.
Yeah.
Really solid information to get us started.
Yeah, I think it's a great jumping off point. So let's get right to it. When you look at all these RF applications, antenna remoting, satellite communications, EW, even radio telescopes, what's that core challenge that they all face? What's the big hurdle?
Well, it all boils down to sending RF signals over distances, right?
Hmm.
And when you try to do that across, significant spans, you hit a wall. The signal starts to weaken, it can get distorted, maybe even lost along the way. And then you have to deal with a huge range of signal strengths all at the same time within the same system. And that's a really tough engineering problem to solve.
It sounds like it, yeah. So that's where this RFOF mini L system steps in, right? Trying to overcome those limitations.
Exactly. And the way it does that is by converting that RF signal into an optical signal. It's basically like turning sound into light and then sending that light signal through fiber optic cables. And fiber, it offers much lower loss than traditional copper cables, especially when you're talking about really long distances. And then at the other end, it's converted back to RF.
So we're ditching the copper, going for the fiber optic advantage. Smart. What are the big wins here? What are we gaining by making that conversion? Because the material you shared pointed out some pretty compelling advantages.
Yeah, well, first off, you get an incredibly wide RF transmission bandwidth. This system can handle frequencies all the way from 1 gigahertz up to 30 gigahertz. And there's even an option to extend that low frequency range down even further to zero point 0.1 gigahertz. That's a massive range. And it's a huge deal for all kinds of cutting-edge applications like advanced radar and next-gen satellite communication.
Yeah, I can see that. You need that kind of bandwidth to capture and transmit a massive amount of data across all these different frequency bands. And you don't want to be juggling a bunch of separate systems to do it.
Right, exactly. Think about how much data we're trying to send through satellites these days. And EW systems are getting so sophisticated. A wider bandwidth means more capacity, more information, and more flexibility to operate across different parts of the spectrum, all without having to build a whole new setup every time.
That makes sense. Now, the next thing that jumped out at me was this term, spurious free dynamic range, or SFDR. I see they're boasting a very high SFDR, something like 112 dB hertz. So, okay, that sounds pretty impressive, but what does it actually mean for someone working hands-on with these RF systems? What's the real-world impact?
Okay, so think of SFDR this way. It's like the system's ability to hear a whisper in a really noisy room, without all the loud conversations drowning it out. Basically, how well can it deal with both really weak signals and really strong signals at the same time without creating interference, or those spurious signals? And in scenarios where you've got a huge difference in signal power, a high SFDR, that's absolutely critical.
I see. So, like in electronic warfare, where you might have strong jamming signals trying to block out faint signals you want to detect. Or in antenna testing, where you have massive difference in power between the main beam and those weaker side lobes.
Exactly, you got it. If your SFDR isn't high enough, the strong signals can create distortions. Imagine it like echoes in a phone call. And those echoes, well, they can mask, even completely bury those weak signals you're trying to pick up. A 112 dBHz SFDR. That tells you this system can keep the signal path super clean. It can let you identify those weak signals, even with powerful signals blasting around. And for you, that means you can detect fainter threats in a contested environment, or get much more accurate measurements in, those super sensitive testing situations.
So a high SFDR, it makes things easier down the line, right? Less time spent filtering out noise, less worry about strong signals overloading things.
Exactly, you hit the nail on the head. It simplifies signal conditioning a lot.
Mm.
You might not need as many filters or gain control stages. And the overview even mentioned that it could, in some cases, eliminate the need for extra preamplifiers entirely. And that streamlines the whole design, potentially saves a lot of cost and complexity.
Mm.
It's also worth noting that RFOptic mentioned that their other high SFDR RFoF solutions, they offer a minimum of 111 dBHz. So this L series, this is top of the line stuff, really designed with low noise and high SFDR in mind.
It makes you wonder what they'll come up with next. Okay, and then there's the low noise figure, or NF, I should say. Why is it so important to keep that noise figure low?
Well, think of noise as static on an old radio. The lower the noise figure, the less static the system adds to the signal. And that's super important when you're trying to detect those super faint signals or keep a signal as pure as possible, like
Mm.
in distributed antenna systems for mobile networks where you need that clear, consistent coverage, or in radio telescopes trying to pick up incredibly faint signals from space, minimizing noise. It's everything.
Yeah, it makes sense. If the system is too noisy, it could completely bury those weak signals. You wouldn't even know they were there.
Exactly.
Yeah.
And like the material points out, a low noise figure, sometimes it means you can skip adding another preamplifier, which keeps things simpler and keeps the signal pure. The datasheet says the standard noise figure is 28 dB at 20 gigahertz, but it also says that by using preamplifiers, you can get that figure much lower, maybe even down to 9 dB, depending on how it's configured.
So there's a bit of a balancing act there, right? Figuring out if you want to prioritize super high SFDR or a really low noise figure, or maybe strike a balance somewhere in between. It depends on what you're trying to achieve.
That's a good point, yeah. And the L series, it's specifically designed to give you that optimal balance between low noise and high SFDR. So they've clearly considered that trade-off.
Okay, let's dig a little deeper into how it all works. In simple terms, how do you actually transform an RF signal into light and then back again?
Okay, so there are two main units, a transmitter and a receiver, TX and RX. The transmitter takes the RF signal and basically uses a tiny laser diode operating at a wavelength of around 1.55 micrometers to imprint that signal onto a beam of light. Then that light signal gets sent through a standard fiber optic cable, which, as we've mentioned, you'd typically provide yourself.
And at the other end of the fiber, what happens there?
The receiver unit has a photodiode, which is sensitive to light in a specific range, around 1.5 to 1.58 micrometers. It picks up the variations in the light signal and turns those changes back into an electrical RF signal. So it's a two-step process. RF to optical, and then optical back to RF. And that fiber optic cable, it acts like a super efficient highway between the two.
Simple in theory. I'm sure the actual engineering to make it all work is incredibly complex, but the concept itself is pretty straightforward. And it seems like they've designed these mini-L modules to be pretty versatile in how they can be deployed. The material mentioned a few different options.
Yeah, they've definitely thought about different scenarios. So you have the standalone module is the most basic form, but they also offer ways to integrate these modules into standard 1U enclosures, the kind you usually find in labs or data centers. A single 1U enclosure can hold up to 4 modules, and there's a removable panel version that can fit either 2 or 4.
Yeah, that's perfect for a controlled lab environment or as part of a larger integrated system. But what about when you need to use this tech in more demanding settings? Out in the field, so to speak.
Well, for those situations, they offer these really rugged outdoor enclosures, IP54 rated, that can hold 2 or 4 units. They've got tougher connectors like MPO optical connectors and different options for data and power connections, things like USB or RJ45 for data and HP sockets or DCAC terminals for power. They're built for places like remote antenna sites where they might be exposed to the elements.
So lots of options for different environments, and it doesn't sound like you're stuck with a one-size-fits-all solution either. There was mention of customization options as well.
Right. One of the really cool things is the ability to add internal preamplifiers and post-amplifiers. That lets you adjust the RF gain, the P1EBB, which tells you how much input power the system can handle before distorting, and the noise figure to really dial it in for your specific needs.
Can you give us an example of how that would work in practice, how you might use those amplifiers?
Sure. So the datasheet gives some examples. If you add a preamplifier, you can get a gain of 3 dB, an input P1 dB of negative 9 dB, and a noise figure of 9 dB, all measured at 20 gigahertz. If you go for both a preamplifier and a post-amplifier, you can get a much higher gain of 25 dB, input P1 dB of negative 13 dBm, and still keep that low noise figure of 9 dB.
Wow, that's a big boost in signal strength. But I'm guessing there's a trade-off, right?
Yeah.
Didn't the material mention that the amplifiers increase power consumption?
Yeah, each amplifier adds about 3.5 watts. So you get more power, but you have to factor that into your system's power budget.
Makes sense. Okay, I think we have a good understanding of the tech itself and why it's so advantageous. Let's shift gears and look at those specific applications we touched on earlier. Antenna remoting seems like a pretty obvious use case.
Oh, for sure. It's all about putting antennas further away from the main signal processing equipment. Think telecom, where you need to place antennas strategically for good coverage, or satellite ground stations where the antenna needs a clear view of the sky, which might be far from the control center. Using RFoF means you can send those signals back and forth with very little loss or degradation, even over those long distances.
And RFOptic specifically talks about using this for satellite communications, right?
Okay. Right, they've got complete solutions, indoor and outdoor, for Ku and Ka band satellite antennas, all the way up to 40 gigahertz. Their outdoor terminals are designed to handle tough conditions and can house up to 6 of these TXRX modules. And everything's controlled over Ethernet. The indoor terminals can be kilometers away, which is great when you can't easily get a network connection near the antenna itself.
Really flexible. And you mentioned EW and radar as well. How does that high SFDR come into play in those fields?
It's a game changer because, like we talked about, you're often dealing with a huge range of signal powers at the same time. In electronic warfare, you might have powerful jamming signals trying to block communications, while you're also trying to pick up really faint signals for intelligence. The high SFDR lets you process both without the strong ones drowning out the weak ones. And in the radar, you need to be able to separate strong reflections from the main target and weaker reflections from, clutter or other objects. RFOptic even mentions using it in radar altimeter testing, where you need very precise measurements of those reflections.
Wow, that's fascinating. And what about distributed antenna systems, or DAS? Those are designed for better wireless coverage, right?
Yeah, the idea is to get consistent, high-quality wireless coverage in a specific area, whether it's a big building, a campus, or even a dense city. Low noise and minimal spurious signals are super important for that because you want to deliver a clean signal to users. RFoF helps with that because it doesn't add a lot of extra noise or interference. That means a better user experience overall.
And for super sensitive instruments like radio telescopes.
Radio telescopes are looking for those incredibly faint signals from space, so phase linearity and low spurious levels, they're super critical. Any distortion or noise added by the system can mess up the signals they're trying to observe. RFoF helps keep that data accurate and reliable.
So they can really see what's out there. And telemetry and general testing and measurement, those were mentioned as applications too.
Yeah, so telemetry systems, which are used for gathering and transmitting data remotely in aerospace, environmental monitoring, all sorts of things, they benefit from RFOS reliability and ability to send data over long distances without messing it up. And in testing and measurement, where accuracy is everything, this tech lets you characterize RF and microwave components and systems very precisely without introducing unwanted noise or artifacts into the measurements.
It really seems like wide bandwidth, high SFDR, and low noise, those are the key strengths that make this tech so valuable across so many different applications. Okay, let's get into the nitty-gritty. What kind of specific performance can we expect? The datasheet for the standard RFoF 30G L0 mini transceiver lays it all out.
Right, so typically measured at 20 gigahertz, you get an RF gain of around negative 18 dB, and the gain is pretty flat across the entire frequency range, plus or minus 4 dB from 1 to 30 gigahertz. The 1 dB compression point is 12 dBm, noise figure is 28 dB, and the SFDR is indeed that impressive 112 dB hertz to the 2/3 power. And they say the maximum RF input level is 16 dBm. Anything higher than that could damage the unit.
There's also a bunch of other specs listed: input and output VSWR of 2 to 1 and very low spurious levels like negative 95 dBm or negative 80 dBc. What's the significance of those numbers?
They're all about signal integrity. The VSWR tells you how well the system's impedance is matched to the devices you connect to it. Basically, how much signal gets reflected back. A lower VSWR, like 2 to 1, means a good match and very little reflection. The low spurious levels, that's more confirmation that the system itself isn't creating unwanted signals that can mess with your measurements.
So it's a really clean signal path.
Great. And what about practical considerations like power requirements and physical size? It uses a 5-volt DC supply, and they list some recommended power supply models. Power consumption is pretty efficient, 2.5 watts for the transmitter and only 0.5 watts for the receiver. That's not counting any amplifiers, though.
Right, of course. And physically, is it a big, bulky unit?
Not at all. It's pretty compact, 75 by 154 by 33 millimeters, and it weighs 450 grams. They use standard 2.92 RF connectors and FCAPC optical connectors, which are common. There's also a DB15 connector for power input and data monitoring. And they even have software you can download that lets you monitor the system through USB. Pretty handy.
Definitely sounds like a well-designed system. Powerful, but still compact and energy efficient. And the data sheet includes a lot of ordering information too, listing all the different configurations you can get with or without preamps and postamps.
Yep, they give you the exact part numbers for the transmitter and receiver for each configuration. Plus, they offer a bunch of accessories, like cables for standalone setups and connector sets for those outdoor enclosures.
So they've really thought of everything. It sounds like a comprehensive and versatile solution.
It really does. The amount of detail they provide, all the different configurations, the accessories, it shows just how mature this tech is, how adaptable it can be.
Okay, so wrapping things up, this deep dive into RFOptic's 30 gigahertz RF over fiber mini L solution has been really illuminating. It's clearly a step forward in dealing with the inherent challenges of those really advanced RF systems. That ability to transmit wideband RF signals over fiber with such impressive SFDR and a low noise figure, it's a game changer.
You know, the thing that stands out to me is how well this combines the best of both worlds, RF and optical. That incredible SFDR, it's essential as signal environments become more complex. The
Mhm.
low noise keeps the signal pure, and using fiber optic transmission means distance is no longer a major limitation. It's elegant, really.
And for our listeners who are all about gaining knowledge quickly and thoroughly, this RFOF solution is a perfect example of that. Whether you're pushing the boundaries of SATCOM, developing cutting-edge defense systems, or doing research that needs the most precise signal handling, understanding what this tech can do, well, that could open up all sorts of new possibilities.
Absolutely. Stepping back and looking at the bigger picture, simplifying signal conditioning, reducing the need for extra amplification that not only makes systems more efficient and streamlined, but it could also pave the way for more innovation and more cost-effective solutions in the future. We're just scratching the surface.
That's a great point, and it makes you wonder, what other fields could benefit from this kind of tech? What about future sensor networks that need to handle massive amounts of data?
Yeah.
Or maybe even medical imaging. Could this play a role in scientific research where you need incredibly precise control and transmission of RF energy?
It's a great question, and it highlights the increasing convergence of radio frequency and photonic technologies. As our need to process and transmit increasingly complex RF signals grows, well, solutions like this RFoF system, they might become absolutely essential. There's a huge potential for new applications here, and exploring those connections could lead to some really groundbreaking stuff.
It makes you excited for the future. Thanks for breaking it all down for us. Really insightful.
My pleasure. Always happy to dive into these fascinating technologies.
Until next time.
See you then.